This is the first lecture of this entire course, and I want to lay the foundation of the object that we're mostly studying. So in this course, like I said in the introduction video, we're replacing in the classical analysis, harmonic analysis, we study the periodic function on the real line, and then we want to replace that by a group. Okay, so essentially, the real line we're basically using is additive structure, so it's a group structure. So we want to replace it by an abstract group. And of course, we need to put a topology on this group so we can talk about continuous function, integration, and so on. Okay, so let me lay basically the foundation of this entire object. This is called the topological group. So a topological group, by definition, is just a group G. So this is a group, and you have a topology on that. Okay, so I'm not going to talk about what's a topology. You should learn that in functional analysis. So if you need some more background on topology, you can go to Laurent Macou's website. He has a nice course note on functional analysis, and he has a brief introduction at the end of his course note. So feel free to read that. Okay, so a topological group is basically you put a group put a topology on this group, and you want this topology to be compatible with your group operation. So in the group, there are basically two operations. So there's a multiplication map. You take two elements, you multiply them, and there's an inverse map. Okay, so the multiplication map, you can think about it as a dot map. That's taking from the product space to G again. So you map X, Y to their product. And similarly, the inverse map is from G to G. And these maps, you require them to be continuous with respect to the topology you put. The inverse map is kind of easy, just G to G, the product, you require that to be continuous. But the product map, you really put the product topology on the G cross G, okay? So it's a product space of two copies of G. They're both topology groups. You put the topology on the product space, and you require that to be continuous. And if you really just want to write it out, what does it mean is essentially saying the following. So for the multiplication map to be continuous, it means if you can find an open neighborhood of any product of xy, so xy is some fixed xy, and you put it inside some open neighborhood, then you can always find two open neighborhoods of x and y so that their product v dot w is contained in U. So here I should briefly say the notation is v dot w is basically all the, I should say v dot w, where little v is inside big V and little w is inside big W. All right, and I should probably also say by convention this V inverse is just V inverse where V is in V, okay? So that's what we're going to use, and sometimes you may see x dot V, that's just left translation of V, so V is in V, and then you do the same for the right translation, okay? So that's our notation. All right, so for multiplication map, that's essentially this is the equivalent to this map is continuous, and similarly for the inverse map. Okay, so that's very simple. All right, so before we talk about their property, let me briefly give you a few examples. So the first example is the set of integers. So you just put a discrete topology, so it's an additive group. Okay, so we're going to see that a lot. And this is essentially, you can think about it as the group corresponding to the Fourier transform of the usual harmonic analysis in the classical sense. And second, I want to talk about is the following. You can think about the real line, or I should put the unit circle here. So the real line and unit circle, they are groups, of course. And what kind of topology you put? Well, you can actually put two kinds of topology. So you can put a usual norm topology or norm topology. So basically that's the topology inherited from this real and the unit circle with respect to their usual metric, the Euclidean metric. Okay, so you put the open set and close as normal. But also you can, well, every group you can put a discrete topology and you always obtain a topological group because under discrete topology, everything is continuous. Okay, so you can also equip them with discrete topology. So just purely on the outbreak level, so the real and this unit circle, just on the outbreak level, they're basically the same group, okay? But what's the difference when you put different topology? Well, the difference is that the continuous function on these groups will be different. So we're going to talk about continuous function, say, on the reals, and continuous function on the unit circle. This is going to be different, okay? They are different if you put different topology, okay? So that's what I mean. All right, so that's why, again, the topology may matter, okay? So depending on which topology you have, some results may differ. All right, and next big example is this class of Lie groups. So first of all, we talk about the GLN of R, the general linear group, basically all the matrices where you are invertible, okay? So they form a group, and you do the matrix multiplication. And this is actually slightly stronger in the sense that, so let me write it, this is actually stronger in the sense that your multiplication map and your inverse map are not only continuous, but also smooth, okay? So think about, you have an n by n matrix, you do their multiplication, each entry is just a polynomial of their corresponding product and sum. So these multiplication inverse, they're clearly continuous, but actually stronger than continuous. They're smooth, okay? And we can talk about their subgroups. So subgroups of these GLN of R, or of course you can do complex as well. They're related to something we call the Lie groups, okay? So this is a big class of examples. We're going to talk about a few Lie groups in this course. And finally, just one example that is kind of omitted most of the time is the topological vector space you learned in functional analysis. So topological vector space is, you can treat it as a topological group as well, it turns out. Well, you basically just think about it as an additive group, okay? You ignore the scalar multiplication of your vector space, just treat it as a group under addition. And it's certainly a topological group, okay? So in fact, topological vector space has some stronger, okay? So it's actually stronger in the sense that your scalar multiplication is also continuous, okay? So scalar multiplication is continuous for topological vector space, but it's not required for topological groups. If you forget about the scalar multiple, then you treat it as a topological group. Now let's briefly go over some basic properties of a topological group. Okay, so first of all, if you have some open set, let's call it U, and you want to pick any x inside G, then the first property basically says you can translate this U left or right, or you can take this inverse, they're still open. And second, if you take a open neighborhood of the identity, so by the way, I use E as the identity in this course. So as long as you have an open neighborhood of the identity, then you can pick something we'll call a symmetric open neighborhood. So this V is another open neighborhood, also of E, and V inverse are the same, and V dot V is inside U again. And thirdly, if you have any subgroup, okay, you can close it up. The closure is also a subgroup, okay? And the fourth one says if you have an open subgroup, then it has to be closed, okay? So basically every open subgroup is also clopen. And finally, if you have two compact subsets, then if you take their product, okay, A dot B, then it's also compact, okay? So let me just briefly go over these proofs. So the first one, this is just really from multiplication, and the inverse is they are continuous. So this is follows immediately from these multiplication map, and the inverse they are continuous. Multiplication map, well, it's joint continuous, so you have it's continuous on the product topology. But if you fix one coordinate to x, and you let the other run on G, so that's again a continuous map. Okay, so that's quite clear. All right, and second, so what do you how you pick a symmetric neighborhood inside this U? Well, so first of all, because your multiplication is continuous, so since this identity is just identity dot identity, and multiplication is continuous. Okay, so from this, you know that you can find two neighborhoods. So this E is inside W1 and their W2, they're both open neighborhoods of the identity, so that the W1 dot W2 is contained inside this big neighborhood U. Okay, so how do you make something that's going to be open and symmetric? Well, you need to take let's take their intersection. And I want to have the set equals to its inverse, so let's do the intersect their inverse, okay? So we know W1, W2, they're open, so by the first property, their inverse are also open. Okay, so now I take an intersection of four open sets. That's all going to be open, so this is open. So because it's open and you can clearly see that V and V inverse, they're going to be the same. And because your V is a subset of W1 and W2, so you do the V dot V, that's going to be a subset of W1 dot W2, which is a subset of U. Okay, so V is a nice enough neighborhood. Okay, for the third property, this is kind of trivial. So if you take any say X is inside H closure, then there exists some net, let's say X alpha inside H, so that this net converts to X. And you do the same for Y. So Y is inside the H closure, so there exists some Y, say, and then you can use the same net, okay, so inside H, so that this Y alpha goes to Y as well. And then you do their product, this X alpha, Y alpha, because it's H itself is a group, so that's going to be inside the group. Your multiplication is continuous, so when you multiply them, that's going to convert to X and Y. Okay, so this is inside H, so their product is again inside the closure. Okay, so that's kind of trivial. The fourth one, so if you have an open subgroup, well, one thing we often do in group theory is you consider all the cosets, okay? So if you consider all the cosets called G mod H, basically all the left cosets, okay? So here X inside G. So we know each of these left cosets is going to be open because H itself is open, okay? And if you recall from group theory that all the cosets, they're going to be disjoint, okay? So two left cosets, either they're disjoint or they're the same, okay? So what you can now see is that H is essentially just G take away all the other left cosets, okay? So you can say this is G, take away the union of all the XH where X is not inside H. So as long as X is not inside H, its coset is not H. But this is open because each of these XH is open. You take their union, that's again open. So you take the complement, so this is also closed. Okay, so every open subgroup is also closed. And the fifth one is kind of trivial from the continuity of the multiplication map. Okay, so your multiplication map is continuous. So if you remember, your continuous map will map compact set to compact. So your A cross B, that's a subset of G cross G, that's going to be compact. So it's the image under the multiplication, which is just A dot B, that's going to be compact as well. Okay, so that's clear. Well, I just want to briefly talk about the consequence of the number one. So here, the number one tells us once you have a open set, you can translate it. So this is, if you recall what you did in topological vector space, you study a topology on a vector space and you often translate to zero, okay? You translate to center at zero, so usually you only need to talk about base, a neighborhood base near zero. This is the same thing in groups, okay? You can also translate things around, so oftentimes we only look at bases near the identity, okay? You can translate everything to identity. All right, so let me just briefly talk about one quick corollary of this proposition. So I have some maps that's actually going to we need to use a lot. So I have the translation map. So let's say LT, that's the left translation. So let's say LTX is a map from G to G, where it basically maps X to left translate by X, so it goes to XY. And the right translation RT of Y, that's going from G to G, it basically maps Z by right translation by Y, so Z dot Y. Sometimes you put an inverse here, okay? Sometimes you put an inverse here so that the LT becomes a kind of a automorphism. You can think about LT maps G to LT of X, so it's G to the automorphism group of G. Anyways, they are both translation maps. Translation, they are going to be translate this entire space. And if you forget about, well, they're not automorphisms of the group, then they're automorphism as a space, so as a topological space. And they're clearly bijective. And because of the first property, these LT and RT, the left and right translation, will map open sets to open sets. So they're both open maps. And because they're bijective, they're clearly continuous. So they must be homeomorphisms. So they are both homeomorphisms. Okay, so this is one little corollary of what we saw.